Okay, thanks very much, Ken. Thanks very much for the invitation as well to give this talk. As I was just saying a minute ago, I really wish I was there with you. So I've been asked to talk about observations of thermonuclear supernovae. So this is obviously a very large topic. So I'm going to give quite a biased talk on some of what I think are the most exciting observations that have come out of thermonuclear supernovae in the past couple of years. So this is a diagram that comes up a lot in observational talks of all sorts of transients, but this is one particularly for white dwarf transients. So it's the absolute magnitude of the transient on the y-axis, and then the decline rate, so how fast they're evolving on the x-axis. And so for normal type 1a supernovae, they tend to lie on this relation here. So this black line roughly is the Phillips relation. And so the idea is for normal type 1a supernovae that we use for cosmology, the brighter events have broader light curves, and the fainter events have narrower light curves. And it's from this relation then that you can correct these and then use them as standardizable candles for cosmology. And so this was all well and good if you want to understand normal type 1a supernovae, which I'll come on to in a minute. But what we've actually found in the past few decades, but definitely in larger numbers more recently, is that there's a huge variety of transients that we think are associated with white dwarfs, so some kind of thermonuclear explosion of a white dwarf. But they cover this huge range of parameter space, so from about -14 magnitude in B band right up to -21. And so any models that want to try and explain type 1a supernovae, we may need different ones, and they need to be able to try and explain this whole parameter space. And so one of the key things we want to do is to match up some of these different types of events that we've put into these classes based on their similarities, and try and match these to the explosion scenarios and the companion stars that are involved. So this wouldn't be possible to try and get these large numbers of events without a lot of state-of-the-art transient search facilities. So I've put some of these here on the map, some of the main ones that are active at the moment. And so they scan the sky looking for new supernovae, which then provide alerts, and then we go and get follow-up observations. So we want to try and get the follow-up observations as soon as possible after we find the transient, because as has already been shown by Abby, these are very interesting observations to get, and I'll discuss them a bit more in a minute. So I'm involved in the Zwicky Transient Facility. It's one of the main transient search facilities at the moment. So it runs a public survey on a 2-day cadence at the moment in optical filters, and then it also runs a higher cadence proprietary survey. So this movie here shows some of the 2018 type 1a supernovae that were presented in a number of papers that are shown here. Johan Yao was the main sample paper, and then Mattia Bulla and Adam Miller had looked at different aspects. But what you can see is that there's a lot of very early light curve data for these events, and they go up to a redshift of about 0.1 or so. And so they have very early light curve data, and this means that we can then try and constrain some of these different models that we've seen can provide clues onto what the explosion scenarios are. And so then just to flag up, we've now completed we have a sample from 2018 to 2020, and so we have plans for a new ZTF data release of the type 1As next year, and so there's about 3,500 type 1As out to redshift of about 0.1. So they don't all have the nice data that are shown here with the very early light curves, but they do all have spectroscopic classification. So this will be a really nice data set that we hope to release soon. Okay, so in this relatively short talk, I'm going to focus on a couple of aspects of understanding thermonuclear explosions. So firstly, I want to look at constraining normal type 1a supernovae, and then in the last few minutes, I'll look at taming the zoo of exotic thermonuclear transients, so some of this diversity. So then for the normal type 1As, this is what a light curve of a type 1a supernova looks like, a cartoon of it. And we want to try and probe different types of physics at different aspects of the light curve. So at very early times, we can look at different signatures of the companion and then of the explosion itself. When we come up to maximum light, We can look at different properties, such as polarimetry. Obviously, that'd be great to get earlier, but it can be very difficult. We can look at the presence of high velocity features and many other kind of broad spectral classifications or characteristics that can help distinguish between these. And then another interesting time in the light curve is when we go to later times, so into the nebular phase. So at approximately 150 or 200 days after explosion, you can start to see into the core of the supernova, so the outer layers become transparent. And so this can then tell you about the core nucleosynthesis. We can also look for companion star interaction at this time. So if you have a non-degenerate companion star, you might be able to see hydrogen and helium that was swept up in the explosion. And then also going back at very late times and looking at the host galaxy studies, so trying to understand the underlying stellar populations, can actually give very nice clues as to their progenitors. So I don't have time to go into much details on all of these, but I wanted to mention two. So one of these is the early supernova 1A light curves. So Abby discussed this nicely in her talk earlier. But there are a couple of different things that we can see in the early light curves that can tell us about the progenitors or the companion stars of type 1A supernovae. So this is a figure here from Dan Kazan's work in 2010. So this is kind of the original idea. And if you look at the very early times, the first few days after explosion, you can see a flux excess in the light curves, depending on what companion star you have. So this is the case of a Chandrasekhar white dwarf that then interacts with a companion star, runs into the companion star, and you get interaction. And so depending on the properties of this companion star and also the viewing angle, you get different strengths in this light curve. So after that, a lot of people wanted to go out and try and find these signatures. These are difficult observations to make. And so this was done in a number of cases. But also on a modeling side, there are a couple of other ways, such as the helium shell destinations, which we heard a lot about earlier, that in some cases for the thick shells can actually produce similar size and shape bumps. You can also get this for different nickel distributions or in the ejecta, or circumstellar interaction as well. So there are models showing that. And so they differ somewhat on their timescales. So we'll hear about from Chris Nee about one object in a little while that has very nice early data on it, but there have been a few that have been found in the literature or that are in the literature that have bumps of different sizes. So if you look at the bottom one here, so this is 19 YBQ that Abby also showed. And so what was key about this is highlighted here in this blue region, is that it had this very early UV excess. This is in the SWIFT bands and also in the more optical filters as well. So that was how it was triggered in ZTF. So clearly has an excess and rises and has this initial decline phase before rising again to the normal peak that we see in a type 1A supernova. So this was very unusual and very easy to pick out. And the other two objects I show here have quite prominent flux excesses at early times as well. So there are a couple of different ways you can look for these, as I'll mention in a minute. And so you can compare to models, or you can compare to light curve templates to try and identify these excesses, but they have been identified in a good few objects. One of the things we wanted to look at in ZTF, because we have such a nice sample of early light curves, we wanted to try and look and see if we could do this in a systematic way in a sample. So looking for, say, less prominent bumps than just these ones that were identified more easily. So that's what we did with a PhD student of mine, Maxine Deckers. So she looked at the early type 1A supernova sample from ZTF. And so the aim here, or the hard part of any of these kind of measurements of flux excesses, is that you need to know what the underlying type 1A supernova light curve is. And so that's hard to do, because when you have a flux excess, you have something on top of it, so you don't know what it is, the intrinsic rise of the light curve is. And so there are a couple of ways that people have used in the literature to do this. So you can use explosion models, you can look at power law fits and any deviations from those. Some people use light curve fitters. So these are ones used for cosmology. You can kind of get a template at a particular light curve width to use as your underlying template, or you can compare to a specific very well sampled event. So this line here just shows 11 FE. So in Maxime's paper, we chose to compare to explosion models. So these are Chandrasekhar mass explosions with varying degrees of nickel. So this gives some of the diversity that's seen in the rise times of the early light curves. They rise roughly as power laws, but they're not all consistent with the t-squared that a lot of people originally thought they would. There's actually quite some diversity. So we compared to some of the explosion models. I think these different methods have pros and cons, but many of them identify similar bumps, although there are some differences. And so these are the colored light curves here are the bumps that were identified in Maxime's sample. And so you see an excess compared to normal type 1a supernovae. And then in the gray underneath here, for example, a 17 CBV, which had a clear bump. Many of these have a similar level of bump. And so overall, we were able to identify that there are, so we got an intrinsic rate of 18% of normal type 1a supernovae, so not the unusual ones. Normal type 1a supernovae have a flux excess in its early light curve. So the uncertainty is large, it's over 10%. But it does look like when you get these very early data, you do see these flux excesses. We also looked at to try and constrain some of the properties of them in a systematic way. And so that's what the plot on the bottom right is showing. So this is the G-R color 3 days post-explosion against the duration of the flux excess. So there are different ways to measure this. We want to try and compare to models. So you can see down here you have the CSM interaction. This is the rough range that will be covered by these models. And then you have the companion interactions shown as this shaded green. And then this purpley blue is the nickel clump model. And so you can see some of the models are consistent with circumstellar interaction. And there's quite a lot of overlap in this parameter space, so this color versus time scale. But some of the objects, so these four black points over here, are inconsistent with the CSM interaction model. So it's hard to tell. As Abby showed, you do need the spectra as well. So that's something we're trying to look into now. I will say they're all inconsistent with the thick helium shell double detonations. The models are just too red at basically all phases. So they're inconsistent with these. So these are smaller bumps or bumps that are seen in normal type 1a supernovae that don't seem to impact much on the properties at later times. Okay, so then other interesting phase is these late time observations. As I said, the late times are really interesting because we can see the nucleosynthetic yields that are going on in the core of the supernova. We can also look for interaction signatures if there's hydrogen or helium material. This is when it's predicted to be seen. And you can also look for asymmetries in the ejecta. So one thing that people have been looking at recently is looking for stable nickel in late time observations, because this is a good discriminant. So if you can measure the mass of the nickel, this is a good discriminant between some of the sub-Chandrasekhar and Chandrasekhar mass explosions. The reason for this is that any of the nickel produced in the explosion itself should have decayed away by these late times. And so anything you see left is stable nickel. And the models that the sub-Chandrasekhar mass models predict lower nickel over iron mass ratios. This is just dependent on the amount of electron capture that's happening due to the different densities in the explosion. But the prediction is that you get lower nickel over iron mass ratios for the sub-Chandra models compared to the Chandrasekhar mass models. And so Andreas Flores had a nice paper on this 2 years ago. So that's what's shown in this plot here. So he measured the mass of nickel over the mass of iron in a sample of late time spectra of type 1a supernovae. And then up the top, you can see the predicted range for sub-Chandrasekhar mass models and then Chandrasekhar mass models. And so this is the distribution of the objects in his sample. And so you can see that overall, there are more objects that are consistent with the sub-Chandrasekhar double detonation scenario than the Chandrasekhar mass. There's some nice, I should highlight, there's some nice work that's being done at the moment. The first nebular phase spectrum, which I'm sure you've seen, has come out of JWST by Lindsay Kwok, and they can make some nice constraints on this as well. I think one caveat with these observations that's come out in the last couple of years, there's been thought about more clearly, is that A lot of this is dependent on the absolute scale of the mass ratio, and so the hard part is converting from the measurements you make of the line fluxes in the spectra to actually go to your masses of your nickel and your iron. And this also depends on the ionization state. So you can make some kind of estimates of what you think the temperature and density of the ejecta are at these times, but it actually looks like there's a lot of variability in that. So I think it is hard to make these measurements. One, I think, nice piece of evidence for likely to contribution from a sub-Chandrasekhar and the Chandrasekhar mass channel to normal type 1a supernovae is the ejecta masses. This is from Richard Scalzo's work in 2014. This is the ejecta mass versus the nickel mass. So the ejecta mass is calculated from the volumetric light curves. So it's not a very large sample, but when you calculate the ejecta mass, there are clearly some objects that sit above the Chandrasekhar mass or close, well, they're consistent with the Chandrasekhar mass of 1.4. And then there's some that are sub-Chandra. So the error bars are quite large. But I think this, similarly to the nebular phase mass ratios of this nickel to iron, also predict that you're likely getting a contribution from both. And this is, I think, what's going on and probably generally accepted in the community now. So yeah, there's a lot of evidence for explosions at approximately the Chandrasekhar mass. So with the early bumps, you can also see a CSM interaction, and there's some properties of supernova remnants that suggest these higher mass explosions. And you also get occurrence in younger stellar populations. On the other side, there's other evidence that suggests that there are explosions of subchandras, white dwarfs, so you can get these nickel over iron ratios, the lack of companion detections. We don't see hydrogen and helium in their spectra, so you need to be able to hide a non-degenerate companion star. And we also see type 1As in all stellar populations. So I think one way to make progress is with larger samples. I think going to the UV at early times is also can also be very useful for constraining these bumps. And then, of course, we want more detailed explosion model predictions as usual. So we've been doing
3 minutes.
3 minutes. Okay. Okay, thanks. So we've been looking at this in CTF to try and expand this sample. So this is just some preliminary work, building up a larger sample. So, okay, I'll move on then just in the last 3 minutes to the exotic transients. So I don't have time to go into great detail on this, and I didn't think I would. But I actually think we've made a lot of progress on the diversity of or explaining the more unusual transients. So I think actually we're worst at trying to explain the normal 1As, but much better at explaining the unusual ones. So I don't have time to discuss it all, but I think with the super chandras, I think we've got a good idea. This is probably slow accretion in a double degenerate system. The 91Ts could be delayed detonations of Chandrasekhar mass white dwarfs. I think it's consistent with the young stellar populations. Some other one, these O2Es, probably violent mergers of carbon-oxygen white dwarfs. And then I think one of the ones that I'm most confident of are the 1AXs. So these are most likely deflagrations of Chandrasekhar mass white dwarfs. And then the normal 1As, well, I don't know. But obviously, as Ken Shen is the organizer of this meeting, I'm going to say it's D6. So just briefly then on the 1AXs. So as I said, these are the ones that we think are most likely deflagrations of Chandrasekhar mass white dwarfs. I think this has been thought for a good few years now. So this is where the deflagration doesn't completely unbind the white dwarf, and so you're left with a remnant at the center of a few tenths of a solar mass. And this has been seen in nebular phase spectra. We also have pre-explosion imaging that suggests the blue companion star, which might be a helium star. And so one object that I've been working on recently is a 1AX discovered very soon after explosion, so within 7 hours of the expected first flight. And so we can put really nice constraints on the modeling with the deflagrations, this N5 def model of a deflagration of a Chandrasekhar mass white dwarf. But one new thing that we want to try and do is try and test for companion interaction. And so when we fit the N5, or not even fit, just compare to the N5 def models, There's not a lot of room for a companion. And so in these single degenerate scenarios, we should actually be able to see it if we're saying it's some kind of companion star. And for the main sequence stars, we can rule out most viewing angles. So I think for these, it's most likely, or let's say it's most consistent with a helium star. We can't rule out all viewing angles. Okay, so I think they're sorted. I know Viraj is going to talk about an even fainter 1AX in his talk. So I think we're doing reasonably well, but we probably need to sort out the normal 1As. Okay, so to summarize, I think, yeah, they're excellent standardizable candles. We do need to make some improvements for the cosmology. We've got good, I think we're making good progress on the rarer classes. And my opinion is that it's most likely that there's two scenarios for the normal type 1As. And we need larger samples and more modeling, as always. Okay, thanks very much.
Plenty of time for questions. Laura.
Hi, Kate. Thanks for the nice talk. It's Laura Chomik. Just wondering if you could say a bit more about efforts to get spectra of those early bumps in the optical light curves.
Yes. Yes, we definitely want them. So we do have some programs. So because they're very faint, they need large telescopes, and then you also need obviously to trigger very quickly. So we have managed to get a few with X-shooter on the VLT. And I think one of the ones that the kind of objects that I'd really like to get would be some of these ones that don't have very prominent bumps, but have some bumps at early times. But it is difficult to do, but we are trying to do it. Yeah, and there are some examples, but it's difficult.
While I'm walking, oh, okay, go ahead.
So thanks for this very nice talk. I guess I have half a comment and then a question about this. My comment is I'm very skeptical that you can make normal 1As from two physically so different explosion scenarios and still make them look so similar. So if that would be possible, then I would assume that in some major observational properties, they have to produce a bimodal distribution. Are there any hints that you see something like this?
Yeah, so I agree with you. I think it is like unsatisfactory to have two different progenitor channels. I think one of the more obvious ways you could divide them up would be on the host galaxy properties. So I think it's clear that we have objects that explode in very young stellar populations, as well as those that explode in old stellar populations. And I don't think there's a good mechanism for having the same progenitor channel for both of those. So I think one of the best ways that we can try and do it for these larger samples is to kind of look in a multidimensional space to see if we can get some kind of multimodal distributions. But we haven't managed it yet, which maybe is telling us something.
Hi, my name is Chris Nee, and with regards to Rudiger's question, I think there are some evidence that there could be bimodality in normal supernovae 1A. With regards to nebular phase iron and nickel emission lines, and also in the early phase, there's evidence for red-blue bimodality, but that may depend on what kind of filters you ultimately end up using. Some people don't find a bimodality if they use relatively broad filters, and then if you use other kind of filters, you may find that there is a bimodality. But I do have a question for Kate. Kate, thank you for the talk. I wanted to ask you about the iron-nickel ratio, which seems to be an indicator for sub-Chandrasekhar explosions. There has been some talk in this conference about calcium production in sub-Chandrasekhar explosions. And the calcium seems to emit in near the same complex as the stable iron and nickel. So something has to give.
Yes.
Right?
Yeah, so you can, so I've looked at this personally, so you can try and model the same complex. They are in the overlapping region. They obviously have slightly different, or they have slightly different wavelengths, rest wavelengths, but they do generally overlap. And most of the models some of the models predict that the calcium should be in some kind of shell. And so you then would see some kind of flat top profile. I think I'm reasonably confident for the normal luminosity type 1A supernovae that we're not getting a major contribution from calcium. But definitely when you move down towards more transitional objects and down to the 91 BGs, I think that there are definitely calcium contributions there. But for the normal 1As, I'm pretty confident that it is just nickel and iron in that region.
Thank you.
Kate, how do you know within hours of the explosion whether it's going to be a 1A with a bump or not to get a spectrum?
So we can't. So we can't even tell if it's going to be a core collapse supernova or not. So the most of the techniques just try and get a spectrum of anything that's very, very young, and then we work it out afterwards.
Okay. Any further questions? Yes, Ivo.
Yeah, this is Ivo here.
Hey.
I'm just wondering, from the past comments about bimodality, some years or maybe decades back, Benetti had this paper about low velocity gradient and high velocity gradient. And the feints are something else, but basically they're both high velocity and low velocity gradient type 1As are normal, right? And maybe that's something else that splits the sample into two, really. Don't ask me which one was which, but or what do you think?
So I think the velocity gradients, I'm sure the modelers can, or the theoreticians can say more, but it ties back to the density profiles in the outer ejecta. So it would work for bimodality if that was a prediction of the different models. But I think they all have similar density profiles, or relatively similar density profiles in the outer ejecta.
Any further questions? If not, let's thank Kate again. Thanks, Kate.